Can you see the screen, my screen?
Yeah, perfect.
Great, perfect. Okay, so once again, thank you very much for coming. And I would like to thank also organizer for this opportunity to present to discuss our recent work with Volodya Bazhanov and Gleb Kotousov. Perhaps the first author of this work should be Gleb. He performed an enormous amount of work, and neither me nor Volodya can compete with him. Anyway, so I'm going to talk about in the first part of my talk, I will discuss the some nonlinear sigma models. Okay, some nonlinear sigma model. And so let's start with, so first I would like to describe the ground we are going to study. Okay, so here's the story. So and in the beginning of the 90s, in string literature, it was discussed the metric of these forms. And perhaps the first who realized that this matrix has share the same, almost many property of the four-dimensional Schwarzschild solution in Kruskal coordinate was Wheaton in 91. And so here is the space-time diagrams for this metric. U and V is a real coordinate, so real numbers. And in principle, you can split the UV plane on 6 domains, as it's shown in this figure. I'm sorry. And the lines, you have clearly see that there is some special lines here. UV equal to 0, define the cross, and this is horizon. And from this form of the matrix, it is clear that there is no any singularity as the curvature is. So it's just a coordinate. So there's the curvature is finite at the horizon. But there is also the space, the singularity at hyperbolas UV equal 1, where the denominator became 0. Well, and also there is no globally defined time coordinate, but in each of these regions, it's shown in this figure, you can introduce the Killing vectors, and this Killing vector field is a space time-like in the domain 1 and 2, and let's say space-like in 3 and 4. 5 and 6 is some mysterious domains. You know, we'll not talk about this at all. So in fact, if you're interested in the thermodynamics as in 4 dimensions, if you're interested in thermodynamics of the black hole, we should the strategy is to perform kind of weak rotation. So we start with the space-like domain 1, let's say, right? In this domain, we can just perform the weak rotations of the time from real to pure imaginary. Everything I'm talking about the target space here. So if you do so, it means we choose some different real sections. So instead, considering U and V as a real coordinate, they will relate it to certain conjugation conditions. V would be minus a complex conjugated on U. And the matrix, original matrix, which has a Lorentzian signatures, became the matrix which I call Euclidean black hole matrix. And this is how it looks like. But I'm a little bit cheating at this point because I forget to include the sign minus here, right? So if you make the substitution to original Lorentzian metric, then you get sign. So I write this sign, and what we get, the metric with Euclidean signature. So it's just a Riemann manifold, and this manifold, it's a 2-dimensional manifold. And this manifolds, it's easy to visualize because you can, it's a simple exercise to embed this metric to 3-dimensional Euclidean space, and then it looks like a cigar. so the point u equal 0. So remember that it's kind of related to the horizon. It's a tip of the cigar. But in the domain, there's also a asymptotic domain where you can neglect 1 compared to squared of u. And in this domain, the matrix resembles a half-infinite cylinder. It's easy to see if we use the coordinate, the coordinate theta and alpha. And during my talk, I also will use this coordinate. Then with this coordinate, the matrix becomes just a flat matrix, right? But the variables, the coordinate alpha should be compactified, right? So if you consider, so this is angular variables. But as a matter of fact, well, in my talk, I would prefer to drop this tip and instead consider the manifold, which is actually universal cover without this point, right? And that would be much that's always useful to do. It's rather convenient. Even finally you can return to the original cigar. All right. So here is the metric. And then once you have Euclidean matrix, we may consider now the nonlinear sigma model. The target space background is very simple. You just has a metric and no other fields. Well, at least at the classical level, right? So it's a classical actions. I include the Planck constant here, h, which is to emphasize that it's that may be some additional terms. Well, if you treat this as an effective action, certain exception dilaton terms, but where at this point we are just on the classical level. So the actions are rather simple, and we can supplement this by boundary conditions. And instead, the natural boundary conditions just periodic, right? So again, let me emphasize that I will talk about for worldsheet, I will use the Lorentz signature. So I explicitly emphasize on this action. I don't use any summations here. It's a T. It's a real time on worldsheet time, and X it's a coordinate, space coordinate, right? And as we consider the boundary conditions, and so I consider more kind of generalized periodic boundary conditions, and include some twist parameter k here. And this is why I actually would like to work on not on this manifold, but on universal cover. So this is a reason why I cut this point. But to have this parameter, it's very useful. It's very useful and from the very beginning. Okay, so this is a nonlinear sigma model, two-dimensional nonlinear sigma model.
Sorry, could I ask? So this extra factor, is it? Can I think about the diffeomorphism, or is it some particular subset of which preserves the form of the metric?
This is just a boundary conditions. This boundary conditions. Boundary conditions, right? To integrate. This is an action, the whole actions. And so in principle, this boundary condition is, if you consider the variations of these actions, then, well, usually it's equal to 0. So this boundary condition will guarantee the total variations, not only the bulk terms, but then the boundary term will disappear. And we can include this twist. It's parameters of the boundary condition. What do you mean, diffeomorphism? Maybe I just missed your point. Diffeomorphism to what? From worldsheet to target?
Because I mean, obviously, metric wouldn't change, right? If you change u by phase factor,
metrics will not change at all, right? Yeah, so that means that I say that principle we should be talking about the universal cover of this. This is why they prepared this point, but I need to cut this point. Right?
Okay.
Okay, so this is a nonlinear sigma model, two-dimensional sigma model, and as usual, and any nonlinear sigma model, it's a conformal invariant, at least at the classical level. So the energy momentum tensor, splits, the scalar component, Lorentz scalar component of the energy momentum tensor vanished automatically due to the equations of motions, and there's two component, spin 2 and spin minus 2, right? And they're galomorphic fields, satisfy I'm sorry, I'm talking about the just the usual Lorentzian world sheet, so it's a chiral fields. So each of these fields depends either of tip light coordinate u or u bar. Okay, and also it's periodic if you even for twist boundary condition, if you consider this twist by the energy momentum tensor, the component chiral component of energy momentum tensor are still periodic, so it will not affect on these boundary conditions. All right, but this is model as general features of sigma model in two dimensions, but the remarkable thing about this sigma model, it also possesses the infinite set of chiral fields, which is with the Lorentz spin 2, 2, 3, 4, and so on, and -2, -3, -4, and so on. So, and these fields, they cannot express in terms of energy momentum tensor, of course, they are not independent in certain sense, but they satisfy similar conditions, and also they form the certain classical Poisson algebra, which I call W infinity cross W infinity algebra. W infinity means the spins of these local fields run from 2 to infinity. All right. So that is some property. So it's just a summary of the properties. So we have a set of chiral fields. They satisfy the boundary conditions, periodic boundary conditions. Still, even we include the twist for the fundamental fields U and E. And then in terms of then since they're periodic, they can be expanded Fourier series, and the expansions and looks like this. It's a usual, so sometimes it's convenient to work with the Fourier components, right? Fourier modes. And these modes satisfy, as I said, since we are to start with the actions, we already equipped with certain Poisson structures, so we can, and the mode would satisfy the certain closed Poisson algebra. And
sorry, could I just clarify this W? I just missed probably this point. Is it like extra fields you add, or?
Yeah, you know, it's some field. I didn't write explicitly construction of this field, but so as for the energy momentum tensor, probably it's easier to understand what's happened. But there are some formulas, so they built out of this fundamental field U.
But it's like in a local way, so just
yeah, of course, they are local field. They are local field in the sense of in terms of expressed locally in terms of this one, like an energy momentum tensor, right? It's but
just is it like U squared and some derivatives?
Yes, derivative U squared derivative, and it will be some denominators like this, because even energy momentum tensor. It's not a polynomial in the sense in U, not differential polynomial, but well, I just didn't write it.
No, it's okay.
No, that is a kind of some rather you can very general way can describe that. Okay, so they form the Poisson algebra, and they satisfy also reality conditions. They are real fields. So these are real functions. And so in terms of the modes, it satisfy the standard reality conditions like this. And also, okay, so once we have this Poisson structure, then that would be the good point to start with the quantizations, because as I said, this Poisson algebra contains in the subalgebra some generated by the spin 2 current. And after the quantization, clearly it becomes the Virasoro algebra, right? So in other words, we can think about, after quantization, we can think about this W algebra as an algebra of extended conformal symmetry, which together with the Virasoro algebra contains some spins with the higher chiral fields, but now quantum.
Sergei, a question. If I remember correctly, there is a Bazhanov term also in this black hole.
No, you mean the dilaton term?
Yes.
Dilaton, but you see, I'm talking about the classical action in these pictures. The dilaton appeared in the next order of 8. Okay, so we are talking about the classical. This is indeed the point, but we are talking about the classical. I would like to just describe formal, little bit formal quantizations of the model using the algebra of extended conformal symmetry.
Sorry, but just in terms of counting degrees of freedom, so there is only one complex function, right? So the W's, they are not really kind of independent from.
Yes. I will see. That's good. Yes, of course, you're absolutely right. Yes, they're, in a certain sense, the independent fields only T and W3, only two fields. All other, in certain sense, will generate it at least from the Poisson at the classical level. They can be generated through the Poisson bracket as Poisson bracket algebra. But if you just restrict yourself on fields 2 and 3, they are not from the closed algebra, Poisson algebra. That's only the point. So that is kind of double infinity, but the most important role in this algebra plays only two currents, W2 and W3.
Sorry to insist, Sergei, but Bazhanov term is the classical term. I don't speak probably.
You probably think you probably keep in mind the Bazhanov model. This is a
no, but the black hole model is sort of the non-compact version of it, as far as I understand.
No. You probably keep in mind that this model actually originally was appeared at the coset of Bazhanov model.
Yes.
With this W, of course, you need to include the Bazhanov term in this. But once you gauge this, that you get the action like this, right? So, and the dilaton is something different. It's a classic. It's a quantum correction.
Different story. Okay, thanks.
Yes. So the model is like it is. You can. I'm not going. I don't want to discuss this coset because we principle you can start with this and forget about everything about the cosets, about SL2R, for example. There are many different descriptions, but the result is these actions, and the principle you can now analyze only the property of this model itself. All right, so that is this is a algebra, Poisson algebra, and as I said, the quantizations, you first observe the W2 modes, which is actually identical to the usual notation for them at LM. They satisfy the Virasoro algebra relations. Now it became the subalgebra of the quantum W infinity algebra. But what would be important for us, this is a kind of crucial point in my talk, the central charge of this algebra must be greater than 2. So the classical limit, as C goes to 2, is a Planck constant proportional to the difference C minus 2. And since it's positive, then the limit C goes to 2 should be taken from the above. And that result, the model, this model which I'm discussing here. Okay, and once we have an idea about the extended algebra of extended conformal symmetry, we can try to classify the state with respect to the reducible representations of W algebra. Highest weight reducible representation. The highest weight is a natural requirement if you would like to have unbounded the spectrum unbound from the below. Bounded from the below, and let me first say a few words about the irreducible representations of the W algebra. Let's focus on the one component, chiral component, because it's tensor product. You can first consider only chiral contribution. Okay, and as usual in such a situation, it's useful to start with the so-called Fermat model.
Sorry, could I ask a naive question? So is it so far identical to the classical one, or centrally extended, or it's only Virasoro part?
If you want the central, these terms actually for classical limits should be equal to 2. So it's already on a classical level. Poisson bracket contains this term with the delta functions.
Yeah, but you consider more general like representations than what you get in classical, or
no. Now I'm turned to the quantizations. Now I'm talking about the quantum algebra.
yes, yes.
So that the classical limit in this algebra can be understood as the limit c goes to 2, but from the above.
But it's only W2. My question is whether there is also modification.
Yeah, there is a relation. Sorry, but there is you can quantize. There is some more or less standard technique how to quantize such as algebra. So they form the certain commutation relations. May be easy to describe them in terms of the operator product expansions. But this is a certain quantum algebra, certain W algebra. That structure is well known. So that is a some which satisfy. This is algebra which it's not a Lie algebra, but it's associative algebra, and all the property which you can imagine it holds true. Did I answer your questions?
Yeah.
Okay, good.
Okay. One question from me. So here it's a bit unusual to go to the limits, to the classical limit from above. Usually.
Okay. I will talk this point. This is a crucial point, so we'll talk.
Okay, but the question is it related to the minus sign which you had before?
Yes, absolutely.
Okay.
Absolutely. That is my point of my talk. So that be careful with this. Yes. Yeah. Thank you for pointing this point because that would be important. Okay. Okay, but now let me, instead of this interesting mode, let's just talk a little bit boring stuff about the Verma model. What's the Verma model? It's a construction that goes this way. So you split your modes of the generators of W algebra on positive frequency mode, right? Remember that is a positive and a negative frequency mode here. And all positive frequency mode annihilate the states denoted by omega, and since the zero modes commute with each other, you can simultaneously diagonalize it, and so that would be characterize the state itself. So it's the highest weight. So in this situation, as Colin already mentioned, that it's only two fields at hand, right? So actually it's sufficient to specify the Verma model. It's sufficient to set two numbers, omega 2 and omega 3, which is eigenvalues of the zero modes for the spin 2 and spin 3. So this is why omega contains only two components. And furthermore, the Verma models of this double algebra can be built out of by the actions of negative frequency mode to the highest vector, to the highest state, right? And so this is only W2, W3. And this is a certain space. I consider this is a formal space, and without any reference to reducibility of the space. So this is clearly it's a graded space, natural grading, right? And this is a level on this space. And since we have all the states are generated by two fields, right? So the number of states in each level, it's given by number of bipartitions. So this is a notations I use bipartitions. So here's generating functions standard. So in the first level, for example, at the zero levels, you have one state. This is the highest state. And the second level, you have two states, which is basically W2 minus 1, W3 minus 1, and so on. So that is the generating functions, and that give you more or less character of the W algebra, of the Verma model. But in general, the Verma for generic values of the heights for the highest weight, for generic value when the complex arbitrary numbers, the Verma model is reducible. But sometimes it became reducible, and as it means at certain levels the null vector appears. The null vector is a state which is at some level which is not zero, but still satisfy the same set of relations. So it's a highest vector. So the Verma model will contain the some invariant subspaces, and in order to get the irreducible representation, we should factor out these subspaces, invariant subspaces, generated by the all null vectors. Okay, and it's a convenient. In fact, the parameterization in terms of omega-2 and omega-3, it's not particularly convenient, but instead we are going to use the another parameterizations. First of all, I will parameterize the central charge in this way. Instead of C, I will use N. This is positive because, and you see when N greater than 0, then this central charge is positive. So it's a parameterize the domain in this once and positive, it parameterizes the domain C greater than 2. Then we are going to use the two numbers S and P. And you see that is the relations. Omega-2 is, by the way, it's just a conformal dimension for the state. And omega-3, so we have two numbers, omega-2, omega-3. For this reason, we have S and P here. And let me draw your attention that if you now consider the highest weight irreps, so I will denote by the curl W the irrep, irreducible representations. With the highest vectors and with the highest state and with the highest weight parameterized by ASP. But S and P, it's a parameterizations of the weight. So if you take a look closer on this formula, you immediately see you can flip the sign of S, right, without any effect on the weight. So in other words, the irreps would be identical with positive and negative S. So it doesn't make much sense to consider. So you can restrict all this. For example, if you consider the real S, it's sufficient to talk about only the positive S.
Sorry, another naive question, just to slow you down a little bit. So from the point of view of quantization of the initial model, why do we need necessary reducible representations?
Yeah, but in principle, we can as usual, you can just decompose in a reducible component, and each component, well, they just classify. This is a way to classify the state. This is why because you cannot not necessarily decompose, consider the representation of SU2, not necessarily decompose it in irreducible companion, can consider the whole space as it is.
But like which irreducible representation will appear in the actual, I don't know, quantum?
Yeah, but the representations, well, the usual logic is you just classify it in terms of the reps, right? And see, and then of course the questions what reps may appear in this decomposition. This is the most difficult questions. This is because this is formal. Now we are talking. Here we're talking about the little bit formal way, just formal math. You know how to describe representations, but how you combine this in the field theory, which is local field theory, right? It's not easy, right? So if you
what would be the criteria? What's the algorithm in general?
The criterion, of course, this should be the local field theory. You know, there should be a sufficient number of local operators. You can introduce action of local operators, and locality is important. No, sometimes the requirements would be also unitarity, locality, something like this.
Mm-hmm. May I ask also a question, Serge? To what parameter in the original theory the central charge corresponds? Do you put a charge at infinity or?
I'm not quite understand what you mean by this.
You give an action, you quantize it. Where is this parameter C?
H bar.
I have a Planck constant, and this is just a different parameterization of the central charge. You see, my Planck constant, it's a group less. It's a 2 pi over the n, more or less. And if you're talking about the dilaton, probably.
Probably you speak about the.
I'm talking about the conformal.
It should be something in it, compactification radius, for example. I mean.
It's in front of the action, Volodya. Just
the action. You know, if you go to infinity in this action, you just have free theory on the cylinder. Yes.
If you're talking about the target space, right? So yes, indeed, of course, the domain where it became flat, and the kind of that of course it's conformal invariant. Of course, if you would like to have actions which is solve the string equation, of course you need the dilaton, but it's a next order. But now I'm quantizing this. If from the point of classical actions, you don't. It's something which is order of 1 in terms of age. But here I'm talking about the quantization. So I'm just building the theory. Try to build the theory, describe the Hilbert space of this theory in terms of representations of the algebra of standard conformal symmetry. And the central charge would be the only parameter in this algebra.
Okay, I think I understand what's going on, but we'll discuss it later.
Yeah, maybe we can return to this point well when then discuss it some.
Essentially, top coupling.
Yeah. All right. So what I said that P and S would be parameterized my representations, and so for a generic value of P and S, the Verma model is reducible. Reducible. So the character is given just as a generating function for by partition. So here up to the some simple factors, dimensions related to the dimensions of this. But also when you play in the game with these models, certain situations where the Verma models corresponding Verman models would degenerate. It corresponds the relations when P and S, so linear combinations became some integers, and then the character. And in this situation, the Verma model became reducible, and for reducible representation, the character is given by this formula. So that is some another, and they also appeared in the space of state. Okay, and now let me describe the space of state. How the space of the space of state of these models now it's well distant, and probably the story starts with the work of Dijkgraaf Verlinde in 91. They used slightly different language without the reference to the W algebra. But then was some unpublished paper, some published notes of Sasha and Alyosha Zamolovich. They discussed this point, including the W algebra point. Then was the work of Teschner and so on, so on. So that is very well-known subject, actually, how the Hilbert space of this model looks like. So they contains two components. So the whole Hilbert space of the Euclidean black hole in NLSM the splits on two components, direct sum, continuous and discrete component. The continuous component is characterized by the state, by the presentation W algebra, but with the highest weight take the continuous values. In fact, I will parameterize, if I use the parameterizations, if parameterize the weight in terms of P and S, then the decomposition looks like this. And this is the composition of continuous component. And the P here, it's a certain V and W are integers, right? N is a parameter of the central charge. And so that is this formula describes the decompositions of the continuous component. And what's the meaning of these integers? We take the integers values, but it's nothing but the U1 charge. Remember the geometry of the cigar. It possesses natural U1 symmetry, so the nonlinear sigma model has a natural Noether currents, conserved Noether currents, and you can quantize it. When you quantize it, you get the discrete spectrum. And you see, and since the Planck constant actually the value of this U1 charge quantized in the unit of Planck constant, and because of non-realizability of the conserved charges, we can actually make a precise relation between the Planck constant and the central charge. And here is the relation. The Planck constant, if the charge quantized this way, then the Planck constant should be an extent as pi over n plus 2, while the central charge is 2 plus 6n, which is greater than 2. So that is the first point. So this is an integer, the meaning of this integer v. So this is just the usual U1 charge. But also you have a winding number. Remember that our boundary condition we are talking about here. And this boundary condition variant with respect to, you can replace q by any integers without any effect of this. So using the stringy language, it means that we should, the W, it's a winding number, so it describes the winding of the string on the manifold. All right, and okay, and finally there is this S here, and the meaning of the S is it represents the zero mode moment of the string mode which propagate to along the cigar, right? But clearly in the geometry, from the geometry of the cigar, that if you have the mode, if you start with the mode with asymptotically described, since you have the asymptotically domain, you have a mode which propagate toward the tips of the cigar, that it should be reflected mode, right? So the stationary state should contain both waves with plus and minus S. For this reason, the sign of S is not actually well defined in the model, and the only meaning has only squared, S squared. It's a meaningful quantity, and that is consistent with this fact that the W algebra, if you split the sign of S here, then the highest weight, remember that this highest weight is invariant with respect to change of sign. So that is why we consider the integrals from 0 to plus infinity. This is direct integral, by the way.
So for the sets, in principle, you can write some expression in terms of the fields as like a charge type of thing.
So sorry, say it again, please.
Like, is there some operator which measures the SAS, or it's just ugly?
S?
Yes.
You cannot measure the S, because you know you can flip the sign. It's not.
I mean, S square.
Okay. This is momento. This is momento of the like a zero mode momento in just.
Yeah, but it's momento like asymptotical. I mean, there should be some exact analog.
Yeah, yes. There's asymptotic domain, so you have a kind of, you can introduce the asymptotic basis, and this is kind of like this is messless, of course, theory, but anyway, that would characterize the asymptotic states.
But you can probably also make it as a combination of some of your W operators, just exact.
W will not change it's inside the models. W fields, it's inside X inside them, so you cannot change S by doing. Well, of course, you can build some vertices, some operators which will kind of change of S. Yeah, the local field, which is with X in the whole X, so it will shift. It will need to include all the states. The W fields X inside only each separate linches of the model.
Yeah, but my point is you can measure it by acting on the highest weight, right, or something like that.
If you act on the highest weight, then you need to this operator should be intertwined between the representations of W algebra, right? By measuring this, by measuring the certain operator, certain local. Yeah, that is a. I don't know. Well, the natural operator which would measure that. It's a good question.
Yeah, I think Jan has an answer, but okay, thanks.
Okay. Anyway, so once you have this space, the energy was given by this, represented by this formula, right? So the energy was given by the sum of conformal dimensions of the states. And this is primary states, primary W states, and then this is a level. That gives you the spectrum of energy. It's rather simple to describe. Of course, the degeneracy, all the levels has a degeneracy. And I just described the continuous part, as also there is a discrete part, which contain the contribution of when the P and S are independent, they're related through this relation. So the corresponding Fermat models are degenerate, and this is just schematical formula. I will not describe it explicitly because it's a rather long story here. And let me just leave it how it is. But
can I ask the question? So is this decomposition looks like Plancherel formula? Yes.
Yes, something
so,
like.
So can I say that it is it just gives basis in a square integrable function on this cigar?
The analog of this in the presentation theories for this something like this, right? Right.
Mm-hmm.
And yeah, this is an analog of continuous series and principal discrete.
Yes, and in that case, S and minus S usually related by intertwiner, and usually it comes as in a certain linear combination. Yes, the orthogonal, right orthogonal basis comes as a linear combination with S and minus S.
No, here, well, yes. In this case, you know, the S and minus S, it's not distinguishable.
Yeah, but I mean, it comes really as a linear combination with a certain coefficient such that you have single values of this function, something like this.
Oh, no, at this point, you know, I should emphasize, we are talking about different things. We'll maybe return to this point later, you'll see. But here, S is strictly positive. You can set S is positive because the S and minus S is not distinguishable.
Yeah.
Probably keeping something from the representation of S into R algebra, something like this. Well, anyway, okay. So let's return to this point later, Brad, because it's. Let me emphasize that I'm talking about C greater than 2 case. Okay. And now the natural questions which you can address at this point: what the partition functions? So the partition functions define the partition functions very usual way that the partition functions trace over this just a certain combination Q some term which is involved the Hamiltonian and the Lorentz spin operators, right? The combination L0 plus L0 bar, it's a Hamiltonian, and the difference of these operators is Lorentz spin. All right, and so this is a partition. We're talking about interest in the partition function. This is the questions I would like to address at this point. And from the very beginning, without any calculation, we can make certain predictions. And the first prediction that the partition function doesn't exist, in the sense that that it's infinite, because it immediately follows from the geometry, right? So since the cigar developed the infinite shape, right? It's non-compact manifold, and so it became asymptotically flat, right? And clearly, so the main contribution to this partition function will come from the same. It looks the same at the Gaussian theory with two bosons. One of the boson is non-compact, another one is compact. If you consider the periodic one, boundary condition, more general quasi-periodic boundary condition. But anyway, this is a Gaussian model, and it's clear that the partition function would be proportional to the size of the zero modes of the non-compact field. So if we introduce the half-infinite cylinder of length, introduce the certain regulators here, which is control the length of the cylinders, epsilon goes to 0, then this logarithm becomes very large. So that would be the size of the zero mode. Then the partition function would diverge in this way, and where this is represent the zero mode domain, and then the rest part, it's kind of universal in sense it represents the partition functions of the Gaussian non-compactified field, and one of the compactified maybe more general. This one. This is just a simple, and but of course this is so it's infinite. But of course the most interesting question about the terms which is hidden here by the symbol O1, which is something which is appeared if you subtract this this simple divergence, right? If you drop this divergence, which should just represent the non-compactness and this, then of course you get something which would describe the most interesting part of the story. Okay, so
I have a question. So,
yes.
So in the partition function, can there also be a chemical potential for the W3?
This is a good point. You can add the chemical potential, of course, here, right? Because if you, in particular, that's very useful to do, because I'm considered the twist boundary conditions, and for if you in a trivial twist, the partition functions, this partition function, which is, it's not a modular invariant, right? So in order to get something which is transformed properly, you need to add the chemical potential. That's a good point, right? But let me drop this point because in principle it can be done. No problem with this. All right. Okay. So this is a trace. So the partition function can be represented. Can be represent this way. So we have contributions of the continuous spectrum, and we have also the discrete spectrum, right? First of all, the continuous, as I said, the continuous part of the spectrum contains the divergent terms, which is this is divergency, right? This is divergence term, and some. If you forget about this, if you drop this term, then you get some regularized partition functions, right? But first, let me, and these regularizations, that is important, it's an important point, that's regularization, you can think about this, it's effect of infrared background, right? So how you describe your infrared, how you infrared regularizations. So you can think physically, you can think about this infrared regularization as a thermostat, right? We put the thermostat which result the certain density matrix, right? So and write the density matrix in this form, the component in these decompositions would be represent the matrix element of the density matrix. And the usual, well, since we are interested in a stationary state, certain equilibrium state, stationary state, then the density matrix was just a usual logic of Gibbs statistical mechanics. We require that the density matrix commute with the Hamiltonian, right? And that immediately shows that the matrix, density matrix at each level of subspaces, the density matrix would be proportional to just identity operator with certain coefficients, which depend on level in principle. And but strictly speaking, I also need to include here the commutation with the Lorentz spin operators, because here, but okay, so that is my point, that just in order to have, if you would like to, of course, you can organize your background, infrared background, such a way that will not just create, that will not lead the stationary state, stationary equilibrium. And so that is we are talking about the equilibrium situations. And also effect of this, what that would affect on the continuous part of the spectrum. We also have a discrete part of the spectrum. So what would be the effect of these infrared regularizations on the discrete part? The answer is actually, it's rather straightforward. It's nothing. So the infrared regularization will not affect on the discrete component, because this mode, the discrete mode, the discrete component usually can be thought as the localized states in the vicinity of the tip of the cigar. And so it's wave function, better to say wave functional, it's localized in the vicinity of the tip. So what you do in how you regularize your infrared backgrounds, it's not particularly important at this point. So that remains the unchanged, but here, this density matrix, as I should emphasize, that's something which is defined how you introduce your background, how you introduce your thermostat, how you just. Okay, and the story actually start with the interesting story start with the work of Maldacena, Ooguri and Son, where they consider this model appeared in the context of propagation of bosonic string of IDS3, and they actually in the second, I think it's the second part of the works, they present the formula for the partition functions, of this model, and here is how it looks like. It's appeared in this. Appeared in the certain assumption about how you understand the infrared background. I should emphasize from the very beginning.
So is it, in other words, is it scheme independent, or it is?
Well, the infrared divergence. What do you mean scheme independent? It's physical. The physical. It's something physics. It's not ultraviolet divergence where that depends on that some. There should be some physical input in the problem. And then in that work, the physical input was because it's come from the bosonic certain way to understand this model. But anyway, so there's a partition functions, and in fact, that papers, it was calculated by two loops, up to the first order. But the answer actually doesn't. The exact partition functions almost it's two loops. I mean, one loop actually. Well, classical and determinant. They are exact, just a matter of parameterization of parameters. So that and it was confirmed by another papers later, in 2 years later, Hanani, Prezes, and Trust, where they obtained the same result by the slightly different calculations. And also, let me, and both of this paper was considered only the case k equals 0, so without any twist. But the point is, including the twist here is very simple matter, because, you know, this is basically related to the fact that what you need to do, calculate the actions. In the class, if you're doing the one loop calculations, you need to calculate the action determinant. Determinant usually doesn't depend on boundary conditions you imposed, and everything is it's came to the classical actions. And of course, in the action, it's very simple. It's just a twist. You see, this is only the place where k is occurs. So the generalization of this result is very straightforward. So that is a partition functions with the twist boundary conditions. But so this is integral.
Is it actually true that it shouldn't depend on the boundary conditions that determine?
Well, you know, for this situation, of course, no, in general, it's not true, but it's you know, it's a kind of sometimes it happens, like in harmonic oscillators. Yes, of course, it's not usually true, but for integrable system, we consider it. It may happen. Many situations, but in this situation, it's indeed true. You'll see why.
One more question: does it happen something interesting at the string value of central charge, like 26? Because the cigar 26.
No, I don't see. I don't know. Maybe, but not studied this point in detail actually. Because actually, I'm not quite interested about the strings. I'm more interested in some, let's see, spin chains and stuff like this. So, all right. So no, not I don't know. Well, I don't think so. So there's no any special, but maybe this. Okay, but let me. So this is summation of the all integers a and b. And but also there is a singular the integrals actually diverge. You see it contains the theta 1 functions, which is this one. This is standard elliptic functions, and it contains the pole at z equals 0. So in other words, in integration here is taken over the parallelogram in the tau plane. So in the complex plane with this standard parallelogram, basically, right? Tau it's modular parameters related to the q. And so it has a pole, it has a singularity at z equals 0, and another, to get something finite, you need to regularize your domain of integration domain. So you see, you should eliminate the contributions of the nearest neighbors of the point of singularities. And this is what we expect, right? So we indeed expect that the partition function diverge, and this epsilon would control this divergent part or divergent part of the partition functions, which is just due to the infrared regularization. So that is described. This is a mathematical descriptions of this the regularization. Okay, so but once you have this partition function, first what you can do, of course, from the partition function itself, you cannot extract the density matrix, because the density matrix it's a trace of the density. The partition function is a trace. But for the case of the from this formula, if you have this formula at hand, then you can extract the contribution of let's say the contribution of the discrete component easily. And here is the answer. So in principle, doing this, you can extract the contribution of the discrete discrete component, which is correspond to degenerate Fermat, model of W algebra, and it's expressed in terms of characters of a reducible representation. At this point, it's convenient to use some notations, which is due to it's introduced in the work of Ribot and Chamerus, and the contribution of the discrete component with given by this formula. So that is in principle, it can be extracted from the partition functions, but I will make the comment about this formula later on.
Right.
But
So, yeah, would it be okay to make a break now, just already?
just give me the 5 minutes, and maybe I already done, finished.
One small question. So
Yes.
the density matrix will depend on epsilon, or
No. Well, it's already regularized.
it is regularized. Okay.
We already drop it, and we already come on this. Just Koля, we are finished. I'm almost done with this. Sorry. So that as I said, the density you cannot propose you cannot extract the density matrix from the partition functions, because much more you need more information about this. But nevertheless, in the work of Maldacena, Ooguri and Son, it was make some proposal for this density matrix, and proposal was that this density matrix just a thermal density matrix. So thermal, in the sense it's right in here, so it means the identity, it's access identity operating in any Verma models and any actually representation of W algebra, and everything is hidden on whole triviality hidden in the overall factors, right? Rho 0 S, and it was with some intuition from the string theory, with the based on the kind of Liouville well and some stuff like this. I'm not going to discuss it in details, but it was make a proposal that this factors Rho 0 given by this formula. And you see, it's not quite trivial. So it's some gamma functions here. So but then if you trace this with the representations and and you get the contribution of continuous component. And okay, so we are ready. So if we have this formula, then we can take this formula combined with the contribution discrete spectrum and get the following result. So the result numeric shows, calculations show that not coincide. The contributions, the density matrix, if you use this density matrix, and if you can include the discrete set, that's not equal to the integral. So something wrong here, right? And
Can I ask you something probably silly? But Sergei, I'm not understanding how much is the construction depending on the regularization, or in other words, do you have other possible regularization that?
No, if you have a logarithm divergency, if you have subtractions, then you have only one normalization conditions. You can. This is very simple matter to only one. You just the question how you split the contribution divergent part and the finite part. But this is all the divergent part. It's under control. So you see that that's not big deal. So as usual,
you want to say because you have this log of epsilon.
So you can add in principle an ambiguity in this is splitting on the partition functions on two parts, divergent and not divergent. It's only the constant multiplied by all this stuff. It's only one constant, which may depend on n, but it's not depend on q. That's easy. Make the problem question. That's not a problem. Of course, that is not a matter. This inequality is not such a simple, cannot resolve by such a simple way. So, and the way now, so that is here how to, so what should we do? What density matrix? And now, so here is the proposal which we give in our paper about this density matrix. So that is a discrete, so the partition function discrete component, and you have a divergent part, you have a contributions of the density matrix, but this density matrix is quite non-trivial. This is how it looks like. All right, and so that is you see that is very different. This is different than was that in the work of Maldacena and Ooguri and Son. And in particular, some convenient, useful formula maybe it's describe the trace of density matrix over the reducible representation of W infinity algebra. And if you do so, that is more readable formula. then you see that contains the two parts. The first part, which is this one, and this is a Morse proposal. But also it contains some another additional part, which includes some Lurch precedent, and so that is quite more involved. Okay, and here is, let me finish this part of the talk with the numerics. And this is how the comparison of the partition function, the last column, it's integrals. I input factor 2 here, forget about it. This moment I will explain why 2 appeared here. So this is a result of, this is a case k equals 0 and n equals 3, and this is we calculate this. This is represent the integrals, these integrals, but of course we need to regularize it to drop the divergence. And as a result, what we get, this is a set of number. This is a contribution of continuous part of the spectrum. And this is discrete component. The sum of them, you see that is reproduce these integrals, and for different value. And I said that in principle, it's if you tau is small, that required a lot of computer time. And in principle, but you maybe accuracy is not so great here, but you clearly see the convergence of these two numbers when you increase the number of terms you. And also this partition function, I said, is modular invariant. For this purpose, I also include the two basic modular transformations, and you see that under the modular transformation, each of continuous and discrete components, not modular invariant, but the sum is modular invariant. So this is numeric for k equals 0, and this is numeric for k equal for non-trivial k, which is, remember that you have partition functions with the twist boundary conditions. And we can still define the regularized partition functions for different values of tau. Indeed, and still you have a contribution of continuous part of the spectrum and discrete part of the spectrum. And the sum gives you this integral. And of course, this is partition function for k not equal to 0. The partition function is not modular invariant, but you need to include the chemical potential to make any comparison of the type. This point. Okay, so this is a summary for my for first part of my talk. So we propose integrable non-thermal. This is that's not usual thermal density matrix, but it's integrable in the sense it's kind of and this. For k equals 0, it yields a modular invariant partition functions. For continuous part of the spectrum, the Morse density matrix is applicable only for primary states only. That's indeed true. So, and a matter of fact, that what obtained kind of mini superspace arguments, which is applicable to the high states. And finally, some comment about the continuous discrete spectrum. So there are a lot of literature about this, and they appeared in many papers, starting with the Verlinde. And in that paper, it was some almost correct. But it was some they some additional bound for this spectrum. Then in paper of Maldacena, Ooguri, Son, and Hanani Press Truth, it was a formulas, but and later, but all this formula, they're almost correct. But the complaint, my complaint concerned how they count the domain in the summation domain, the edges, the end of point on in summation. This is important. How they're written in all these works, they actually not properly count this. If you use the prescription, you not get the modular invariant partition functions anyway. So now I am kind of confident that the correct formula reads as it is, right? So this formula, which is a numerical data you saw that represented was in table, and it leads to modular invariant partition function. Okay, so that my more or less probably I should stop at this point and finish in part 1.
Okay, thank you very much. So, okay, we'll take a break for 10 minutes, but yeah, you're welcome to stay and keep on with the discussion.
All right, I will take the first.
Yeah, yeah, of course.
Sorry, Sergey, can you recap one more time? How is this?
Just a moment. May I take the coffee and then
Okay.
go back?
So Sergei, could I ask a question, please?
Can you hear me? Yeah.
Yes. So just a really quick sort of recap of where we are maybe would be helpful. So you introduced these non-periodic boundary conditions, if I understand correctly, and those are parameterized by the parameter k?
Yes, that is with boundary conditions in general.
Exactly. And the statement you are making is that if you evaluate the partition function in the spirit of Maldacena, Ooguri and Son, that you get somehow the wrong answer?
No.
Maybe I misunderstood.
Partition function is absolutely correct. No. My statement that the density matrix is that's not quite correct. The density, you see, you have a partition function. That is a correct. This is modular invariant partition. No questions about the partition.
Mm-hmm.
The density matrix contains something more detailed information about the thermal state, right? So,
sure. And so, could you remind me? Sorry, because what is the property that the density matrix of Maldacena et al. Does not satisfy with these funny boundary conditions?
The partition functions, it's a trace of density matrix model.
Sure.
Roughly speaking.
Yeah.
So of course the trace, the partition function itself, it's modular invariant. No questions about this result. Then that was it's a difficult, you know, that is a remarkable intuitions in the paper. They was able to extract even for the highest state, they extract this matrix element because it's rather non-trivial. You see, mathematically it's very well what they did, but the physical intuition perfect there. So they calculated the factor, which is this combination of gamma functions. And this is correct for the highest state, because basically the intuition was based
highest weight state,
highest weight state, and the intuition was based on the mini superspace analysis, more or less, which is they give the correct answers. But the point is, and then they said, okay, it might, as I understand the logic, that if the matrix density matrix just should be the Gibbs density matrix, just the usual. The usual argument of statistical mechanics when you say that in equilibrium, right? For subsystems, the entropy should be additive logarithm of so entropy should be the additive integral of motions, and in general for general systems, the entropy is the only additive integral of motions, the Hamiltonian Lorentz spin.
Mm-hmm.
But this is something, some additional integrable structure actually present here. For this reason, the density matrix not necessarily, if you wanted a kind of generalized Gibbs ensemble here, but not in the so naive way as usually people doing, including the local integral of motion. I always complained about this point. The density matrix, the generalized Gibbs ensemble is something more involved.
Yeah. So what property does what property of the density matrix does their density matrix not satisfy? So like physically?
No, the density matrix, the Gibbs density matrix, it's a very in general the condition of equilibrium require that the density matrix will commute with the Hamiltonian in some integrals of motions, right?
Mm-hmm.
Additive integral of motions, and then the logic and statistical mechanics, then the logarithm of the density matrix should be additive integral of motions. And for general systems, there are not too many integrals, additive integral of motion you can imagine. But in this situation, that it's something special, right? So for this reason, the density matrix, it's not a Gibbs density, but kind of generalized Gibbs.
Sergei, but generalized Gibbs, you mean in which sense? That there is extra something?
For integrable, see, if you have some integrable structures involved, that you have some chance to add something which is looks like additive integral.
Beyond chemical. Mm-hmm.
You have to add them to this to the distributions to them in this sense, and that not necessarily so naive as an adding of local integral of motion.
Mm-hmm.
Including the local in the integrable system, indeed, that only local integral of motion maybe there.
Right.
principle, they are local, and the local integral of motions. Yes, you have a set of local, mutually commuting set of local integral of motion. That in principle, that is good candidates, but it's not whole story. This is why I complained about all this business with the generalized Gibbs ensemble, so that the situation maybe integrability may be much more involved. That's not so simple.
Mm-hmm.
Maybe
so is the statement that there will be extra fugacities associated to these?
No, fugacity you cannot write. You see, you have in mind probably that you have additive integral of motion, which is just the integrals over the local density. This is right, and like integral over the density of charge, for example.
Yeah.
Right? And density maybe for integrable system you have another local integrals. That's usually not a case for general systems. But that may be more like if you want, it's unlocal in certain sense, unlocal integral. But it's still you can add them because they possess this additivity property for the system. For the local,
but they come with an extra parameter.
Yeah, but in these situations we have this partition function that this parameter is fixed. Probably you can organize more general partition functions, but for these partition functions which is written, but you see we can include more some extra parameter. But how it calculates in path integrals point of view, you calculate the certain path integrals, and we probably may include some terms, extra term to do. If the operator commutes, you can always add with the Hamiltonian. It's natural to add to the additional.
I'm just realizing the time. I probably will continue asking questions at the end.
Yeah. Okay.
Sorry.
May I also ask a question before we start?
Yes.
Sergei, I wanted to understand this expression for the partition function. Which includes the sum over A and B.
I will share the screen probably, right?
Well, I remember. Well, I mean, I only want to understand the very basic question. I can guess from share for the others. It would be good. I can guess and get an idea from where the sum over A and B could come from the ADS side, but I'm just curious from where the sum over A and B comes on the CFT side. By the way, we see your screen, but it's some book, теория неизвестно чего. Какая-то, Галуа. Да, можно было догадаться, но я не догадался.
Now do you see it? Can you see it?
Но мы теорию Галуа до сих пор видим.
Другой десктоп.
In the share window, there is a choice of windows. Probably.
Sorry. Yeah.
Now we see you.
That's my favorite topic, theory theory. This I I read it before sleep. You know. This is okay. Let me see what's going on here. Yeah.
Володя, привет.
Привет.
Так я все-таки тебя, я по 2 раза каждый вопрос задаю, извини. Про C равное 26. Да, про центральный заряд понятно, конечно. Это
там расширение
радиус компактификации.
Нет, тензорный импульс, он содержит...
На английском, пожалуйста.
Sorry. Analytic continuation of my greeting. Okay.
So the energy momentum tensor for the model, of course, contains the term which you call the Churchill infinity. It's extended.
Yes. So that's not.
Otherwise, the central charge should not equal to 2, right? So
yeah, of course.
But it's again, it's a central charge greater than 2.
But I wanted to ask you, do you have some connection to Sine-Liouville theory? I mean,
this is exactly, yes, of course. This is Sine-Liouville. This is identical to Sine-Liouville model. This is a regime where this non-linear sigma model is identical. It's just a dual descriptions. It can be described in terms of the dual field, and the sine Liouville, that's exactly the case. So we are talking now, we're discussing the model which is sine Liouville.
Yeah, that because for a particular central charge, namely for 26, yes, we had this statement that there is a matrix model which is dual.
You're talking about, yes, of course, but we are talking about exactly the same as
That's why I asked whether you noticed something interesting, because maybe some results can be compared.
No. But you see, but you're talking about. I'm talking about the sigma model. You're talking about the strings. You need to include in principle, you need to include the host Liouville, and to make the total central charge to be 0, right?
Sure. That's why I say 26.
But my point is we are focusing only on the sigma model side. You know that is our geometry. The worldsheet geometry is fixed forever, right? It's a cylinder, and that is nothing. I don't know what would be effect of this density matrix. It's a good point, right? Because usually we are rather naive. We are gluing the create this fields and treat the different part of the strings almost separate, right? The host and they somehow just combine it. But you see that is a so partition functions of the model is just the product of them and then integrated over the modular parameters, right? I'm not sure, you know, that maybe it's maybe for critical strings you're correct, but in principle, what I see here that we have a non-trivial density matrix. Why it not happened? The same story happened for the, let's say, for the host and. I don't know how you glue there.
That's why
maybe I just not understand the string theory at all. Not, but in principle, in this picture, right? So the density matrix is not just so simple. It's not identity operators in the IREP of W algebra. It's a different the value. It's identity only on the level. On the levels of spaces. But for different levels, it's different.
No, I understand. But still, for this central charge, there was a calculation on the with Liouville. It was really the sine Liouville of Greg Moore, which we compared with matrix model results, and it coincided, and that's why it was announced that it's a dual model. So, it would be interesting to review this. Greg Moore's calculation from your point of view, whether it was.
But you see, the partition function, not touch the partition function is the same correct. If only the partition function occurs in this question.
Actually, we only pretended on the partition function.
But if the partition function in the strings is just a product of partition functions, so that I will not it's not make any difference because the density the partition functions are the same. But the point is that. It's not a terminal in the usual sense. It's not a terminal in usual sense, but in terminal density matrix, it's just exponent of a Hamiltonian and maybe Lorentz spin something. And that's it, right? But here you see, and that it means so for different levels, it had they're always just identity for if you at levels of spaces. But here you explicitly see, well, in order to get the modular invariant partition function, you need to change the contributions from different levels.
That I understand. Of course, the result which we can compare with matrix models is only the full integral over moduli, yes, because you speak about
if from the string side, it contained only the partition function, that nothing changed, you know. So that is but so that will not change. But if more delicate, I don't know, maybe more delicate quantity is possible. Maybe I don't know how to test this density matrix another way. So the only so I will explain how this density matrix, where did this matrix come from, and in the next part of the talk. But But I don't know really any other checks of this result, only the modular invariance or modular invariance of partition. So they produce the answers, the density matrix, and leads to the partition functions of Maldacena, Ooguri and Son partition functions, and this partition function is modular invariance. That's my statement.
Yeah, but unfortunately in the matrix models, this information is lost because you integrate over moduli.
Yeah, you integrate it, obviously. Usually
Sorry, Volodya, I think we should restart.
Okay.
Maybe can we postpone the discussion after?
There is a second part. I thought it.
Yeah. No. Sorry. No, there's a second part.
When do we stop?
When?
Because I have just two parts that I have to go in half an hour. Okay.
Well, we can talk later at any time.
Okay, better.
It's not a problem.
Let's call each other. Yes.
Yes, that's not a problem.
Mm-hmm.
Okay, so let me find the. So otherwise, we'll study the Galois theory. I can find from my. Where is it? Okay. Okay. Escape. Share the screen. Share the screen. Share. Okay. Okay. File. View. Into full screen. Okay.
Okay, please, whenever you want.
Okay, so should I start?
Yes, please.
Okay, so now let's start the second part of my talk. I will talk about the spin chain. Actually, I will try to well, just to give you an idea how this density matrix we discussed in previous section was obtained, and in the first part we discussed only mostly we focused on the certain nonlinear sigma model. And let me start the second part with some prehistory. And so there are many interesting applications of nonlinear sigma general two-dimensional nonlinear sigma model, including the string theory and some condensed matter situations, and some work which is rather old, right? It's a Zenbauer work, 1999, was proposed some nonlinear sigma models which describe the criticality of the transition between the plateau on quantum Hall systems, and the quantum Hall effect to the disordered electron gas. And in that work, I borrow some some words, some sentences from that work, where there was formulated rather clearly one of the basic principles. So here it is. So in trying to, so it's author own words. And so in trying to solve the statistical physics problems at hand, we have to be very discriminating about which functional integral to accept as well defined and which do not. In concrete terms, we are looking for the field theory defined over the Euclidean to space with the target space of Euclidean signature. This constraint eliminates Candidate's theory with an action functional that is bound neither from below nor from above, and whatever. So then this idea about the Euclidean, so we should in the case of, let's say, Lorentzian signature, non-Riemann signature, the path integral is it's not well defined. Well, it's not clear how to understand these the path integrals in general. And it makes this restriction for practical point of view. It's very natural. However, if you think about the origin model, like a Pruskian model, and all this business for the come from so-called replica trick. And in principle, there is no reason this condition about the Euclidean signature, it seemed to be too severe. All right. And also another interesting information you can extract from that paper of Zinenbauer is that the Pruskian model shares the same infrared behavior as a certain dimensional, one-dimensional spin chain. And this is a rather special spin chain, and its degrees of freedom take value at alternating sequence of the modulus of V and conjugated modulus. But this spin chain, it's not integrable in the usual Yang-Baxter sense. And as far as I understand, there is little progress toward its solutions. Nevertheless, appearance of such alternating spin chain promoted the interest to the so-called integrable critical alternating spin chain. So integrable, it's clear why integrable, because, well, that gives them some tools to study the systems. Also critical here, it's important because usually if you consider some kind of alternations of the system, you get the gap. So the spin chain with the gap, and it's not very interesting for descriptions of the universality classes of we are looking for. Alternating I already explained, right? So the spin chain. So that was some studies, and perhaps the most remarkable output of study of this alternating spin chain was conjectures made by Ikhlef, Jacobsen, and Saleur in 2011 concerning the certain integrable spin chain, and this spin chain is related to for 6-vertex model, so-called inhomogeneous 6-vertex model, which is a special case of the latest model. It's more general integrable systems, latest system introduced by Baxter in the beginning of the era of integrability in 1971. So that is some particular case. So this is how the conjecture looks like. So they propose, they make the following proposal. So they consider the field theory set up here. It's a model we just discussed in the previous in the previous part of this talk. It's a black hole sigma model. Sometimes it's called self-2R or /U1 model. And they propose that this conformal field theory underline the critical behavior of the latest Hamiltonian, of the latest system, which is one-dimensional spin chain described by the Hamiltonian, and it contains the parameters gamma. It's anisotropy, kind of anisotropy parameters, and actually this proposal was based on early observations that this spectrum of the system possess it's critical and possess the spectrum of conformal dimensions of the system of the CFT underlying the critical behavior of the spin chain possess the continuous spectrum of scaling dimensions. That was the earlier works, and then finally there was some attempts to identify the conformal field theory, and that was the final attempt was made in this remarkable paper. Okay. But once you okay, so that is a that's not only the dimensions, but the author presents some highly non-trivial arguments, including numerical evidences that indeed the infrared behavior of the spin chain, the infrared behavior described by the action whose classical action we discussed. But the question, the proposal raises immediate questions, and actually these questions were already formulated in the, it's indicated in the abstract, right? You see, the Hamiltonian which is written here, it's not Hermitian. It contains I. Well, and the point is that if you diagonalize, if you take this Hamiltonian finite lattice, then you immediately see that it contains the complex energies. And that means that there is no, you cannot introduce any, the Hermitian conjugations, which is consistent with positive definite inner product, with respect to which this Hamiltonian is Hermitian. Of course, you can introduce the Hermitian conjugations, but this, the corresponding inner product would be not positive definite. That's my point. So I is crucial, you see, and the model, it's not Hermitian in the usual sense, but SL2R, the Euclidean black hole, the model we discussed before, it's a perfectly unitary theory with a positive definite inner product. So that is the questions immediately arise, and well, but in principle it's not so bad, because let's say in field theory we use, for example, the Pauli-Vilas regularizations, and which is not unitary, right? Which broke the unitarity, but nevertheless the unitarity restored in the scaling limit. So the same type of argument you can use to say that why the starting with the Pruskian model, the infrared behavior controlled by the nonlinear sigma model with the Riemann target space manifold. So in principle, that not kill the proposal, proposal of Jacobsen, Ikhlef Jacobsen Saleur proposal. But however, if one were not to simply brush aside the issue with unitarity, it could be taken as a signal that the IGS conjecture is not quite correct. All right, and then if you start to think about this, then you can you can find the possibility that the NLSM description is still works. It still maybe there's some interesting candidate, but for describing for describing the scaling limit, but with the non-Riemannian target space background. And so that is very interesting, because that would open a way, because assigning the meaning of quantum NLSM, whose target space has a Lorentzian type signature, and since we have if you have a spin chain that we under control, we numerically can investigate the problem. That is that makes of course the path integral is not still maybe, but if you have a spin chain, that is a good point. Okay, sorry, how to close this? Okay, and so actually that was a motivation. So clearly there's such a possibility, interesting possibility, gives it's very interesting in context of the black holes and another applications. So that's basically the motivations of this work. So now let me explain, give some explanations about the most part of this of the discussion. I will focus on explanation the original idea, original proposal of the Ikhlef Jacobsen Saleur proposal and how it works. So let me explain how where did they get the model. So the model is defined in principle. It's related to the usual 6-vertex model with the standard Boltzmann weights. You know, this is a 6-vertex. This is matrix satisfy R matrix. It satisfy the Yang-Baxter relations, 6-vertex R matrix. But instead of considering the homogeneous 6-vertex model, we will talk about, we should consider the unhomogeneous versions of this. So the spectral parameter which you can assign associate with the vertical line. So this is a graphical representation of transfer matrix. It's one row, a single row transfer matrices, and the spectral parameters, it's alternate. So the spectral parameter beta, which we use beta here, the spectral parameters, it's and this line is beta, then beta minus I pi over 2, then again beta, and so on and so on. Then we consider the twist boundary conditions. I include the twist that would correspond to the twist boundary condition for the Hamiltonian, and then finally we build this this operator which acts in the vertical on the vertical sides of this chain, and then trace over the sum over the auxiliary the indexes which represent the auxiliary space. So this is a single row transfer matrix. It depends on the of the anisotropy parameter gamma, and then to get the Hamiltonian, which was already appeared in my transparency, we need to consider the two-row transfer matrix. That is one, take logarithm derivative, and at certain point which is related to anisotropy, it gives the Hamiltonian. So that is a Hamiltonian. Okay, and once you have a, so this is 6-vertex model with the whole properties of Young-Baxter integrability, and it allows us to introduce the Bethe-Ansatz equations, and then we perform and do the all numerics. In particular, the Bethe-Ansatz equations look similar to the homogeneous Bethe-Ansatz equations, but it's slightly different. The factors here, you see, maybe you can see that it's little bit the driving terms is different than usual. Then you take this solve this, take these equations, try to find the roots of this Bethe-Ansatz equation. Then the energy, you can calculate the energy. This is usual, but also you need to consider some additional operator which is called quasi-shift operator. It's called, and I think it's, I don't know, actually I'm not, maybe I'm not quite correct here, but this name appeared in this its work, but in principle such type of operator was introduced in the early days by Fadeev Volkov, and this operator is nothing but the transfer matrix of the homogeneous 6-vertex model, but on this 45-degree rotated regular square lattice. So it's represented in this picture, in these pictures. And but let me emphasize, this is homogeneous 6-vertex model. So these operators commute with the Hamiltonian. It commute with the these operators expressed in terms of the single row transfer matrices, but this way. So it commute with the transfer matrix, single row transfer matrix commute with the Hamiltonian. So then it means that once you solve the Bethe-Ansatz equation, you can calculate the spectrum of the separators given by this formula. Okay, and this is very important object. Now, and that was the following, what might say following observations, that if you take these quasi-shift operators, and let's consider the B, and and consider the logarithm of these quasi-shift operators. Then it was observed that the spectrum of these operators is quasi-continuous in the certain sense. Namely, for as n goes to infinity, it's given by the formula like this. So let me explain how it works. So in usual 6-vertex models, homogeneous 6-vertex model, the vacuum is filled by the beta roots. All the beta roots are located on the single line, right? On the real axis. Well, at least if twist is sufficiently small, then all the beta roots are real. In the case of for the vacuum at least, or maybe in the sector is a different spins. But in this situation, for this model, the situation is a little bit different. We have the vacuum is filled by the beta roots on two lines, on with imaginary part beta equal to 0, imaginary part beta equal to pi over 2. This is related with the clever way of alternating. right? So here we have a we adjust this alternating by the half period, more or less half period, because this sign of this component is not important. The half period of the Boltzmann weights, and that makes very special situations. In particular, in these situations, the vacuums is filled like the pictures like these for the states, which I call the primary beta states. So you have two lines. Of course, they're not for all beta states. It's just some special class of the beta states. But some of the roots will located on the lines in beta equal to 0, some on the line beta equal pi over 2. And in principle, you can the system possesses that two symmetry, and you can interchange these two lines, right? It would correspond to different beta states, but the same energy. It's clear, right? The energy doesn't depend. So that is kind of related, somehow related to that to symmetry, which is present in the this spin chain. The action of the two symmetry it's quite non-trivial on the local spins, but in the sense of the beta ansatz equations, it's very simple. You just reflect if you have a solution of beta ansatz equation, then you can consider reflecting with respect to the line in between of the strip, right? Interchange the strips. All right, and then for such a states, for such a primary states, the number of roots on the top and the bottom won't be different, and the difference between them, of course, integers. And for the state like this, the large n behavior, then you can increase the number of n, would behavior of the quasi-shift operator, to be precise, the logarithm of quasi-shift operator would behave, it's the k with logarithm over the n with the coefficient proportional to the integer m, which coincide with the difference between number of roots at these two lines. So that was observed, and in this paper, I guess in 0.6, maybe I'm not quite sure about the reference, maybe early in 0.5 even. But anyway, so that is a property, and then that's important. Why it's important? Because if you focus now on the energies, then the energy is given by the spectrum of the Hamiltonian, namely, to be more precise, the scaling part, because the energy, of course, contains in the spin chain contains some divergent part, which is linear diverge, but it doesn't depend on the size, or depends on the size of the system, but that doesn't depend on set. So we just take the difference with respect to the ground state. Then the differences decays as a 1 over the n with certain universal terms. This is standard pictures of the criticality for the spin chains. And so this is the spectrum, the states, the dimensions of the states which appear, the universal part would describe by this formula where P and P bar related to the sector of spin sector as Z. Also, that depends on the twist parameter K, which is can introduce the twist boundary conditions, but also include the winding numbers. I call the same winding numbers here. It's also some quantum number which is not present in the lattice system, but appear in the scaling. In principle, you can introduce this winding number, and you clearly see that the spectrum follows this one. But there is some interesting terms. This story almost the same as a homogeneous cases, the XXZ spin chain in critical regime. But here the situation much interesting because we have additional term S, and S here it's nothing. It's turned out, you can check it, that it's decay. It's related to the eigenvalue of quasi-shift operators. So in principle, as n goes to infinity, it's turns to be 0, right? But very, very slowly. And you see this logarithmic decay. You see for any finite lattice, this terms is order of 1, right? Because only logarithm n. And furthermore, you can choose, for example, m, make it sufficiently large, and then this term will be clearly seen in the spectrum. Right, and then what you can do, then we can do a very rather clever way to organize the scaling, and namely we we are going to, since m, it's a parameter, it's a number, quantum numbers, but it's this quantum number is in our in our hand. So we can increase this number simultaneously with the n in such a way to keep the ratio fixed, right? And this is some special prescription for to achieve the scaling limit. But if you do so, if instead of considering S as a running coupling, you consider them as a RG invariant, you organize your RG trajectory in such a way that keep S fixed, while n and m goes to infinity both, but simultaneously to keep this parameter fixed, you get something which would describe by this formula with S is fixed, and of course the parameter ES in the scaling limit becomes a continuous. And that makes the CFT underlying the critical behavior of alternating spin chain has a continuous spectrum of scaling dimensions. And you probably recognize the formula for the dimensions of spectrum of energies in the model we discussed in the previous part of the talk. This is it was the first signal about the appearance of the nonlinear sigma model in this business. All right. But of course, it's it's only the energy. It's not. But then the questions, once you have a continuous spectrum, then the immediate questions returns to the problem: what would be the density of such a state? If you have a continuous component, this is a that what we need to answer first. The question you need to study first, and if you have sufficient imagination, then the principle you can guess the following idea. The following idea maybe may explain. Okay, so if you take a look on this formula, you see that the formula m is integers. There looks like an quantization conditions for the particles in infinite well potentials, and well with the length proportional to the logarithm n, right? Remember that is a formula from the quantum mechanics. But of course, this is not exact formula; it's just a asymptotic formula. It should be some correction here, and like on a well potential particle in the well potential, then the corrections comes from in quantum mechanics. They come from the phase shift, which occurs in near the tuning point, right? And then remember the such a problem from from the textbook of quantum mechanics. Then how to encounter the density of states, such a problem when you increase the size of the system. You first need to find the phase shift of the tuning point, then the quantizations, then the spectrum became discrete, right? So that gives you quantization conditions, and and in principle, once you know this phase shift, then the density of states is defined through the derivative of the phase shift, right? And then the question about the phase shift, and of course it depends on the winding on the spins, and it was a remarkable observation by the IGS due to the IGS that this phase shift has this form, and has this form, and then principle. So if you take this form and substitute and find the density of state, and then of course you can compare this with the numerics, and here is the numerics. So if you take of course you need to subtract this storm logarithm, you regularize somehow, but then the finite part, this is a picture for finite part. This is actually R0. It's maybe without these terms, and you can do this for beta roots, of course, from the numerical data, extract this, find the eigenvalue of beta of the quasi-shift operators, and then using this data, extract, let's say for n equal to 200, then 400, extract the density of state, and you'll see they clearly see the convergence to this formula. So with a very good accuracy, actually. This is very impressive, right? So that's not just a matter of very rough quantity like a conformal dimension, this is something more non-trivial, something really non-trivial. And let me emphasize that what we this density of state describe the density of states, which is pictured on this form. So we just consider the beta states, only the primary beta states, which is which beta roots patterns looks like this. M is a difference between them, and then see how the density, then calculate the Lorentzian behavior and see that that indeed they described by this formula, and then extract the phase shift from the numerical data. So, and if you ask me where did they get this formula, of course they get it from the paper of Maldacena, Ooguri and Son. So they observed then if they take the phase shift, the density matrix from the Maldacena, Ooguri and Son, which was then indeed they reproduce what we get from the spin chain. All right, and so that is a picture. This is so remember that how the S here, yeah, right, and identified with this zero mode momenta S, and P, it's related to the wind. So this formula, which is already see this formula clearly as that it would be U1 charge, and in the spin chain you have clearly U1 symmetry, and so like an Euclidean black hole, nonlinear sigma model, also winding, the twist, everything. So every match, and it can and works for twist boundary conditions, not only the periodic. Well, the parameter n here, right? As let me remind you that parameter n here is related to the anisotropy here, right? Anisotropy of spin chain. So everything looks perfect. Okay, however, the immediate something wrong with the IGS conjecture. So when I first learned these questions, my first question was about the Z2 symmetry. Exactly the questions, because in the spin chain we clearly see that Z2 symmetry. You can construct the operator which is commute with the Hamiltonian X on local spin. It's not highly non-trivial X on local spin, but from the point of view of the beta and those equations, they're quite clear. So if you have the pattern like this of the beta root, then you interchange of these two lines in between, you sweep these two lines, and you get the different beta states, right? So you can construct this beta state on the lattice, for example, diagonalizing the Hamiltonian, and they're different, they're distinguishable. But in the field theory side, from the field side for the NLSM, the S, it's not it's not observable. It's only the certain you see the sign of S is not observable at all. So clearly something wrong here. That there is no Z2 symmetry. Another questions I already mentioned, but maybe it's not so terrible. That the lattice Hamiltonian is not Hermitian in usual sense. It's not Hermitian in the usual sense. But the NLSM is Hermitian. Okay, and later, so when we start to study this problem with the collaborations with Volodya Bazhanov, Gleb Kotousov, also Sergei Koval, it's a graduate student of Volodya Bazhanov, was involved in this business. Then we found that we actually studied the density of state not for the primary beta state, not the state like this, but for some excited state, and we found that the density of state it's not consistent. It's not consistent with Maldacena Ooguri Son density of state. And at the time we believe that the Maldacena density of Ooguri density of states is correct one, and then we explicitly state in our conclusion of our paper that that something wrong with the IGS conjecture, that it cannot be taken literally. But clearly, you cannot just forget about this conjecture because the evidences with this is rather highly non-trivial, right? So that's a question. Okay, and now, now I should explain. So what should we do? How we should work with this? In principle, we need to calculate the density of state, but not only for primary state like this, but also for all descendant states. How to do this? In principle, the quantization conditions, which resemble the quantizations of the particles in quantization condition of the particle in the well potential, include the phase shift, but this phase shift depends on the state. And this phase shift, which was proposed by Ikhlef, Jacobsen, and Saleur, it's correspond to the only the primary beta states. But in general, it's not true. And but in principle, the existence of such quantization conditions is a kind of miracle, because usually in quantum systems, interacting system, we not expect that just one particle quantization conditions would be holds true. But here it's something special. We have integrability, we have a lot of integral of motions, and the beta kind of separation of variables, and the beta states, low energy beta states, actually eigenvalues not only for Hamiltonian but the whole commuting families. So that principle doesn't looks weird. It's not, but and in principle, so the question is how to calculate the phase shift. And the problem, in fact, the problem was solved in our work with Gleb. Quite well, half a year ago, probably. It's based on some machinery which I called ODE IQFT correspondence. I'm not going to just use it in the propaganda. It's really a very powerful method which allows one to do something which is beyond the any other integrable other methods. And in particular, this is a problem where it shows this whole power. So it allows one to calculate this such a phase shift within the ODE QFT approach. And the result, finally, we calculated it for each. You can do this for each beta state, let me emphasize. But of course, in the scaling limit, you should sum over the all beta states. And for individual beta states, it's rather complicated expression. But once you sum all beta states, you get the density matrix, which was already appeared in the first one. So the density matrix looks like this. And this is a result of which is once again it follows from the counting all the phase shifted for beta states for the chain. All right, and so that is why the density matrix, where we get this density matrix, and then once you have this density matrix, you can check that indeed leads to the modular invariant partition functions. Now, so the lesson what we learned, that the conjecture holds true, and the Ikhlef-Jacobsen conjecture holds true. So in particular, the contributions of the continuous part of the spectrum in the Euclidean black hole and the continuous spectrum of the spin chain, they're related by the factor 1/2. And I already explained the factor 1/2 here. It's appeared because of the Z2 symmetry. Appeared because you can, for example, you can say that you can, if you restrict yourself on the Z2 invariant sector, then the relation would be indeed the partition function would be the same. And there's also discrete component in Euclidean black holes, and the same story happened. Some discrete component, some discrete state appeared in the spin chain. I didn't discuss it at all, but anyway, the relations it holds true indeed. I should emphasize that this is a conjecture. This is not whole conjecture of the Ikhlef, Jacobsen, Saleur. It's just a weak form of these conjectures, which is works for any K, by the way. But the statement that, however, the Euclidean black hole NLSM does not underline the scaling limit of terminating spin chain. So in spite of this remarkable relation between the partition function, the Euclidean black hole does not underline the limit. And well, there are many different arguments, and now I'm quite confident with this. because probably the most direct way to see this, you study the finite size corrections to this formula. The finite size, so this is not whole story because it's energy, so just asymptotic series, and you have a terms which is a finite size corrections, and these terms correspond to presence of irrelevant perturbation. They control the how the system approaches to the fixed point, and in principle, and the study the irrelevant perturbation immediately shows that indeed the spectrum, the theory, the underlying conformal field theory is indeed possess the invariance with respect to W infinity algebra, but with the central charge less than 2. With the central charge less than 2. And once you accept this central charge less than 2, this is not the case. Remember that in the Euclidean black hole, the central charge was greater than 2. If the acceptance so, it's naturally resolve all the issue with the two symmetries, unitarity, because in the case of C less than 2, the natural metric, the metric which is consistent with in W algebra, it's not positive definite. The situation is similar that we have in Virasoro algebra. It's central charge greater than 25, it's positive definite. But once you consider the sig less than 1, so-called complex Liouville, sometimes Rudy called, then the metric is not positive definite. So so what happened here? So now to explain what happened here,
Sergei, just could you give us some time estimate, because we're over time already, but just to know.
Okay, well, I can stop. Well, just I can very briefly stop. Yeah. So that just to show you the.
We can have like a little break, so people who are like rushing somewhere, you can maybe pre-summarize and then continue more informed.
Okay, actually, I need 5 minutes or maybe 7 minutes.
All right, that's good.
So this is a double algebra for the black hole, and this is a formula which describes the central charge and heights with respect to heights for in terms of the parameter S and P, and rate decomposition shows you for central charge greater than 2. Here, for the spin chain, the situation is different. The central charge is given by this formula with T minus 6n plus 2, and this central charge is less than 2. But remarkable, if you parameterize in this way, as in terms of S and P, the conformal dimensions are the same. You see, it looks absolutely the same. But the difference occurs for the W3 weights. So it's not as for the Euclidean black hole, it's even function of S. For the spin chain, it's odd. And for this reason, the state with the S plus and minus S are distinguishable in spin chain, but and not distinguishable in the Euclidean black hole. But all the other formula looks very similar. This is why they may confused. While the confusion with dimensions and stuff like this may occur. Okay, and so what's the problem? The problem probably was made. The problem was can be interpretation of this is we should return to back to the weak rotations. And remember, when we perform the weak rotation, we neglect the sign. But this is important. The sign is important. Actually, the sign formally it's appeared here, and that and at least in the formal levels, it leads to the Euclidean black holes. The central charge is greater than 2, but for Lorentzian black hole, but treating as that the central charge is less than 2. The parameterizations, if a Planck constant parameterized like this, then the central charge would be given by this form. So that's a signal that maybe the good candidate may be the Lorentzian black hole. And there's the principle at classical level, you can perform all this that you did for the Euclidean one, still have a sort of currents like an energy momentum tensor, but you have also double algebra because it's fully algebraic constructions. So for this model also have these properties. And clearly you can, from this section, you clearly see the Z2 symmetry. This just interchange U and V. But the question, where is U1, right? Clearly the model is not possess the U1 symmetry, which is present on the spin chain. But fortunately, the answer is rather can be easily understood, because once you introduce U and V real, we cannot take the twist parameter here. K is real. There is no twist parameter in the room. So if you believe that this is somehow related to the spin chain, the twist should be K equals 0. But in this case, as K equals 0, the spin chain possesses some extra Z2 symmetry, which is called C invariance, and which is not commute with the rotations. And once you can restrict yourself on the C invariant sector, that the rotational symmetries break down, and only remains symmetry is rotation of 180 degrees. And then it corresponds clearly, you can identify this additional Z2 symmetry with the simple symmetry of the action when you flip the sign both U and V. Okay, so that is the story. So in principle, the Lorentzian, the spin chain, it's not described, the spin chain, alternating spin chain, not described by, in spite of the remarkable relation between the partition function, it's not described by the critical behavior, it's not described by the Euclidean black hole. Nevertheless, there's a good candidate that is described by Lorentzian black hole. And there are some evidences that there's at least not whole Hilbert space, but at least a part of this space, Hilbert space of the spin chain and critical spin chain and the scaling limit coincide with the Hilbert space of this model. But of course, this is model, it's not, there is no alternative definition. So it's kind of, you can think about the definition of this model using the spin chains. Okay, and there's some important, I didn't mention this and already over time. But in principle, some interesting insight can be obtained when studying the mini superspace approximation for the Lorentzian black hole in the spirit of the mini superspace approximation by Digigraph Verlinde, and that gives you some interest, additional support of this proposal. Okay, so that is basically what we return.
Mini superspace is gamma to some infinity type of thing.
No, mini superspace means then you forget about these terms and consider the quantum mechanics. Then it describes the quantum, the particle propagating on this background.
And for spin chain, what is
quantum mechanics? And when you write this quantum mechanic, you need to find some interesting features, namely the falling to the center, the problem with the unbounded Hamiltonian. That's very interesting. It's very simple, but very interesting quantum mechanical situation, which is probably discussed sometime in classical mechanics, because it's falling in the center. You know, this potential is unbound, and then you need some regularization, and then you'll see how the regularizations appear in this model. Infrared regularizations manifest itself in this model. So that is
this mini superspace approximation has been treated by Jacobsen, Verlinde, and Verlinde.
Yeah, they discuss in the context of in particular in terms of the Euclidean black hole, where this straightforward. Here, this much a little bit more interesting. They discuss how to write there's some delicate point with the dilatons, how to, because you need to properly account the dilaton. So the Hamiltonian in this case is so-called dilatonic Laplacian, and it's discussed in this Digigraph Verlinde way. But the qualitative picture or the physics it can be understood within this approximation way. Well, not whole details, but very useful. So and these considerations indeed support this idea. And you see remember that at some point there should be some infrared divergences there, and indeed you see this infrared divergence in how to handle this. So that basically the point. And so I didn't talk. It may be very interesting from the to get the physical intuitions useful. It's very, this would be very useful. Okay, so anyway, so that is gives some, well, some principle, some road, gives you some road to study the nonlinear sigma model with the Lorentzian type signature, and maybe useful for understanding the physics of the black holes, because it's now Lorentzian black holes, and which is interesting. Okay, thank you.
Okay, thank you very much for the very nice talk. So I'm gonna unmute everybody. Let's thank our speaker. And then we have time for more questions.
Yes, I have a question.
Yeah, go ahead.
So in the even in the scaling limit, your density of states seems to depend on more than the quantum numbers of the primaries.
Yes.
So is that in contradiction with the Virasoro symmetry?
No. This is a way, you see, the Virasoro symmetry. No, it's not a contradiction, because if you we have a critical systems, right? We have a conformal symmetry, of course, but of course extended conformal symmetry. The algebra of conformal symmetry is it's more than just like in the Vesuzumina-Witten model. You have a Virasoro symmetry, but also you have a Kac-Moody algebra there.
Yes, but should then the density of states shouldn't it be uniform for across Virasoro modules, or?
That's what I said. That's what I said. That in general, for general quantum, for general non-integrable situations, you expect that your density matrix is just a Gibbs density matrix, right? Just so it's the same. But the conditions, the equilibrium condition is the density metric commute with the Hamiltonian, but not necessarily coincide with the exponent of the Hamiltonian. It's not it's additional assumptions made. It's not contradict the conformal symmetry at all, because the density matrix commute with the Hamiltonian. But you know, the usual logic and statistical mechanics said, okay, so we have a density matrix, then we can build the entropy. The entropy should be additive integral of motions. And for general statistical mechanics systems, then there are not many integral additive integral of motions. Then if you split your system on subsystems, then you add the entropy, right, from the subsystems. And for general, that's only the Hamiltonian, momenta, maybe some charges and stuff like this. But in integrable system, where if you have some additional integral of motions, a special situation like you have a local integral of motions, that in principle, which would be additive, since it's they're local, so they integrate of the subsystems, right? So the contributions are additive in entropy. The contribution are additive from the different subsystems. And this is why you can, they give you the possibility to consider the grand canonical ensemble, right? The more restrictive for integrable system, but that's not maybe not so simple. And this is an example when you see the density matrix, and it still commute with the Hamiltonian, so it's still identity operators in the each level subspaces, but not the identity in the whole Virasoro modular.
Excuse me, may I clarify this point? I simply don't understand, or I'm interrupting someone.
No, please go ahead.
Yes.
Thank you. So I simply don't understand how the question is formulated. There are many states which commute with the Hamiltonian. Just to say that you're looking for the density matrix which commutes with the Hamiltonian does not specify it uniquely.
Yeah, but I'm looking for the density matrix which leads to the modular invariant partition functions.
That is also not well defined. The density matrix by definition has trace equal 1. right?
Well, yeah, you're sure. Well, it's not quite, but it depends how you normalize it. In my normalization, it's the density trace of the density metric inside the partition function.
Right, I understand that, but I understand. But my comment essentially means the following: you can take any density matrix you want, you can divide by the trace of the density matrix, and then multiply by your favorite partition function.
No.
So,
but it's then the partition function. It's a function for modular of the modular invariant of the norms on the not actually the density. It depends on the temperature, right?
well, Sergei, all I'm trying to say is the following: if you require that your density matrix to commute with a Hamiltonian and the trace of this density matrix to be whatever you want, whatever function z you want, that still does not define this density matrix uniquely.
Yeah, I am absolutely agree with you. But first of all, we can define the density matrix as it defines as a certain path integrals. It's not a game with the normalization. You know, the density matrix can be defined the path precisely in terms of the, let's say, path integrals, and in particular when you're doing the string theory regularization as Maldacena, Ooguri and Son did, then they obtain the certain density matrix, which is functional modular parameters. And this is a modular invariant partition functions. I absolutely agree with you that the density matrix itself doesn't define the partition function doesn't define the density matrix uniquely. But once you have some idea, conjecture about the density matrix, then the partition function is unique. And my point that the density matrix, which reproduce the Maldacena, Ooguri, Son partition function, modular invariant partition functions, it's not thermal one. It's not Gibbs one.
Yes, yes.
That's my point. And but it's not the formula I gave you. It gives just numerical evidence that this is the same. That they produce the partition function of
right.
collaborators. But of course, that's just an evidence. But then I show you how this density matrix was obtained. It was obtained from the spin chain. And this is a result of calculation in spin chain from integrability and stuff like this. This is my observations made. So if you take this density matrix whole, not just one element, but whole density matrix. Fortunately, in the lattice, we can calculate the density matrix. Because there is no correlation with regularization. If you're doing the spin chain on the finite lattice, you already infrared regularized. You know, they're very specific way to handle the system. But if you do this regularization, then my statement, you get the certain density matrix, and the density matrix exactly reproduce the partition functions of from the strings.
Okay, that's good. But my question is just about the definition. I want to understand in both cases. In the case of the spin chain, how do you define the state? Density matrix is a state. There are many states, right?
Okay, good.
And let me also ask the same question on the gravity side. On the gravity side, density matrix is a path integral over a geometry with two boundaries. So I'm not asking about what is the evidence or how you derive things. I'm ready to trust your intuition or your results, whatever. I just want to understand the definition. What is the density matrix you're calculating?
Okay,
actually, it was pretty confusing for me also. So it would be nice if you could clarify this.
Okay, so for the okay. First of all, let's start with the spin chain, right? For the spin chain, right? We have a systems in the case we have a system. I'm sorry, where is it? My for the spin chain, this is integrable spin chain, and the crucial point that for integrable spin chain we have a very special set of the eigenstates, right? The states which is diagonalize the Hamiltonian, but also diagonalize the whole commuting family of operators. So that is a beta states. That when you solve the beta and those equations, you get by very particular basis in the space of state. So here it is. Okay, no. Very particular basis. Okay, and my statement that the spectrum, and this is a situation that you can think about when you put the system on a finite lattice and consider low energy states, then you already regularize, you already provide a certain regularization. So the size of the lattice, the number of sites, would be the parameter which control the infrared control. This is infrared regulators. And my statement that once you take the beta states, for given beta states, spectrum of the quasi-shift operators, which is appeared in the energy, it's related to the energy. It's quantized. This is the quantization conditions, and this quantization conditions the same as the quantization of just one particle problem with the certain phase shift. And so this is for these quantization conditions for beta states, for given individual beta states. Then if you find this quantization for individual state, then that provides a certain basis, you know, they provide a certain basis in the conformal tower, very special basis, it's so-called integrable basis, which is diagonalize the set of local integral of motion. It's very special basis in the conformal tower, because in each level you have a huge degeneracy, right? But the integrable structure allows one to introduce the special basis and calculate the corresponding phase shift, and then sum over the all state in the given level, and that gives you the density matrix. Of course, it gives you the density matrix for the spin chain, and very particular. So that's my point.
Excuse me. Once you have this integrable basis to specify the density matrix, you need to tell the weight, right? Let's say you have a basis
level.
No, if you once you have
for the state.
Once you have the basis, let's say you label the basis elements by the.
Okay, I see your point. You see, in this case, you have a set of transfer matrix, right? It would generate in the scaling limit. It would generate the integral. It would be Hamiltonian, as I already showed. But it would also generate the so-called local integral of motion, the operator which commute with the Hamiltonian. And they act invariantly in each level subspaces, and you can diagonalize the whole basis of local integral of motions, and it gives you particular weight of the state. So to specify the individual weight in the conformal tower. This is very special specializations of the state. But finally, since you're interested in only you not need to count the individual state. You should sum over the all contributions and the result with this formula. But the answer that for calculation, you use particular integrable basis, which is consistent with certain integrable structures.
So the weight is provided by the transfer matrix?
That provided, you see, they have a local integral of motions. For example, if you have a L0 and already another integral of motion would be the integrals over the current W3. But then you can build let's say, some combination, the spin 4 field, like a double squared of the energy momentum tensor plus derivative of the energy momentum with certain combinations of them. And then also the current W4, which I not discuss here. And this combination gives you the local integral of motions, which commute with the Hamiltonian, and and actually this is integral of motion occurred in the scaling limit of transfer matrix.
But I still don't understand. So you have this basis, which is beta states, but in order to compute the density matrix, you need the state, not the basis, right?
But we have explicitly operators, but principle, it's you need to in principle you don't need to, you need not only need to know the spectrum, that's enough for calculation of the phases. But of course you're right, but in principle we have an explicit construction for this for the operators, which allows you to construct the basis, which is diagonalization. In each level, you can introduce the commuting family of operators, this finite matrix.
No, this is fine. But my question, okay, we have this basis. What's next? We're still density matrix correspond to a particular state. Okay, you can expand the state with respect to your favorite basis, but what exactly the coefficient?
Then, since you calculate the phase shift, right? You under control the all states, right? So you can then you to get the density matrix to the density of states, you just sum over the all beta states at the given level, and that is a formula
with the coefficient 1.
With the coefficient 1, of course, because the density matrix commute with the Hamiltonian.
But any of those states are commute with the Hamiltonian. Any of those states are eigenstates of the Hamiltonian. So if you sum them with an arbitrary coefficient, it's still
no. But the density for different beta states, the coefficient, but the density of states controlled for density of the beta states, given beta states, right? They're controlled by the phase, and then they should sum over the phases. Some contribution of all states in the given level. No. You see, this reduces the problem, just one particle problem. You see, you can imagine this just you have a particles, not set of non-interacting particles. You'd like to say, but you're interested on the total density.
But I think the question is before you reduce it. So before reducing the problem to something simple, what is the problem? I think I don't fully understand.
No. And the latest, but we see. Okay, let me put it this way. Suppose you have a lattice system, right? Why don't we calculate the just partition function of lattice Hamiltonian, consider the scaling limit? Well, let's take the Hamiltonian, take a trace of the space and consider the scaling limit of this object. And what I said, that it's given by the formula, which is the same formula as a Maldacena, Ooguri and Son proposal. That's my statement. That's in the scaling limit. The scaling limit, the partition function would be indeed inside.
So you take spin chain with a fixed lattice spacing, compute partition function, take lattice spacing to infinity.
We do this. The parameter of infrared equalization for the spin chain would be the number of sides.
A number of sides.
So n is 1 over the epsilon. The epsilon is a regulator, infrared regulator for the sigma model. But my statement that in spite of the number of states the same, but they're not the different theories.
Maybe I'm wrong, but I have an impression that what happens is the following. You have an integrable system, so in principle you can have multitude of different generalized Gibbs ensembles. All of them will be commuting with the Hamiltonian. And somebody asked this question in the beginning of the talk that, of course, you can have a lot of fugacities which parameterize those space of generalized Gibbs ensembles. My understanding is that you choose a very particular generalized Gibbs ensemble, which you essentially guess or derive, but it's a very particular one with only a few fugacities involved, such that the trace of that guy matches the partition function of Ooguri Maldacena. So essentially, you're discussing very specific generalized Gibbs ensemble, which from the point of view of the spin chain is not mathematically specific. It's not unique in any way.
For the spin chain, it's very specific. It's very specific. In principle, you can, but you need to do something extra for the spin chain with the boundary condition I imposed. That depends on boundary condition also. But for the chain, for the fifth boundary condition, that's very specific. Of course, you can imagine something.
When you say very specific, maybe we're lost in language.
One conjecture into another, essentially, or
for the latest systems, once you put in the finite box and specify the boundary condition, you have a matrix, and not everything is specified.
Yeah. When I say specific, I probably I didn't mean concrete. I mean that it's not. There is no without reference to this work Ooguri and others, there is no a priori mathematically special way to define this generalized Gibbs ensemble.
This is not, I'm not agree, because let's take the Hamiltonian. Let's take exponential, make an exponential, take the trace, and latest Hamiltonian. You get some number for the function of n, and then you consider the scaling limit. N goes to infinity.
Sorry, I think so. There is just to clarify. So you just take standard Gibson, not the generalized one, just standard Gibbs ensemble.
But you see, but standard. But we have a very special situation. We have a spectrum, continuous spectrum of dimensions, and that makes you what's standard, what's not. It's you know, the spectrum of dimensions is continuous. And you have an intuitions which you have a discrete spectrum, then there is no questions about this.
No, on the spin chain. On the spin chain, you just take standard Gibbs ensemble or not?
In the continuous limit here, we have a spectrum of dimensions is continuous, right?
No, that's fine, but before, on the regularized, on the...
but I'm talking about the scaling limit.
Yeah, but
before this, of course, there is no, everything is discrete, but the complex, the energy is complex.
But I think Anatoly had a problem when everything is discrete already, that there are many Gibbs ensembles one can generalize.
Yeah, but you see, the double, it's hidden, it's in the spectrum is continuous, how you perform the scaling limit. You see, it's a very delicate point. If the system like a XXZ spin chain, like a discrete spectrum, that's more or less no, there is no room to play the game. But here, you see, as I said, the scaling limit, it's not a simple matter.
No,
and once you have a continuous spectrum, then
you can confirm, just to answer Anatoly's question. So if we have finite regularized spin chain, do we just compute e to the minus h and then send the number of sides to infinity, extract log, and we are happy? Is it
but it would diverge. You see, this quantity would diverge. The anomaly scaling would be there, because it's usually you expect that would be modular invariant object appeared, but here with the divergence, logarithm and divergence, there's some anomaly behavior of the partition functions, anomaly scaling of the partition functions, and this is why this is signals from the continuous spectrum, and this is the same problem we have in the from the nonlinear sigma model. Formally, it's diverge. Right, so it's infrared diverge and it's infinite. It's that's it. But in principle, you can say
but before it diverge, is it standard Gibbs ensemble or generalized? That's the question.
That I said that in principle that you in string theory there is some principle, right? That your partition function, it may be diverged, but you regularize, but you should regularize such a way that it should be modular invariant.
Yeah, which translate into standard Gibbs ensemble or into
that I said that you if you follow these prescriptions from the strings for the nonlinear sigma model, if you would like to have the modular invariant partition function, that the corresponding density matrix is not just a Gibbs matrix.
I think I think I understand your question. You answer in the following way: if you just consider the regularized spin chain and trying to consider thermodynamic limit, it will not be described by a CFT in the thermodynamic limit. But if you start modifying the Hamiltonian by other conserved charges and fine-tune coefficients of those conserved charges, which you add to the Hamiltonian, then in the thermodynamic limit, this ground state of that system, the form system, will be a CFT, and that perhaps uniquely defines the values of those fugacities.
Yes, yeah, that may be formulated in this way. I think it's right, but the only point I just a little bit worry about what you say about the fugacities, because it's not. Once it may be confuse people, because fugacity usually you couple the fugacity with the local integral of motion, and I don't understand how mathematically rigorous describe this point. How you can this object that's operators which I introduce here. That's so-called reflection operators.
Right.
And
Yeah.
this is a kind of object which is not quite, I don't know how to express in terms of fugacity.
For the sake of, as far as I'm concerned, we can call those fugacities coupling constants because you deform the Hamiltonian with these guys.
In the right sense, that's you're right. Yeah.
And this terms you introduced, this the reflection operator, it doesn't have to be local operator.
Yeah, it doesn't have to be local. And the principle from this point of view, the transfer matrix itself, it's generating functions of, you can think of the combinations of the local charges with the certain coefficients of fugacities, right? The transfer matrix itself. It's a generate so that my point is the object with the sum of the fugacity is something wrong with this. It's not a, so mathematically this object doesn't exist. Which my impressions, because if you just take the local integral of motion, sum of and naively consider that the sum, that is it's not well-defined mathematical object.
I think it wasn't very crucial in the Anatoly comment whether they're local or not.
Maybe, but
my basis of commuting operator.
Principle here you have something which is not once you have a continuous spectrum that you maybe not well that's some delicate. It's a once you have infrared divergence, and it clearly that it's some physical problem. It's not a matter of regularization and ultraviolet divergence, which is you know, that's something artificial. But infrared divergence always signal about the physics.
Right. So we broke the record today by half an hour at least, the duration of the talk.
Right, probably.
Maybe can continue in more private settings.
Yeah.
So let's thank the speaker again. Thank you. All right. So I will stop recording.